So, typical things that you will do is you will start with alpha 0 equal to delta, but then you will compute what is known as alpha q, and this q is essentially the iteration index, right? So, this is depending upon, you will begin with q equal to 0, in q equal to 1, you will compute the alpha based upon this equation, and that alpha is going to be multiplied by delta, and that is going to help you determine the sequence. So, okay, so typical process of what is the value of xq plus 1, that is going to be equal to x0 plus alpha q. Okay, and let's make all of this equation clear with an illustrative example problem, but the key idea is you will see that we are taking an alpha, which is basically some value which is larger than 1, and multiplying that by delta, and that is essentially added, and that is helping us getting broader, bigger and bigger interval bounds to search for, which is typically bigger than the Swan's method that we have. Okay. So we begin with x1 plus delta, then we start with x2 is equal to x0 plus a alpha 1. So if you look into how do we compute alpha 1, so the alpha 1 will be coming from this equation here, right, the equation that we have here. So if I look into this equation, right, if I want to write alpha 1, that should be equal to sigma j goes from 0, and since we are interested in finding 1, right, so this will go from 0 to 1, delta of 1.618 j, right. So that's what is written here. So if I take j equal to 0, the first thing should be delta 1.618 and j is equal to 0. So that gives me the first term, and then we will change this j and make it 1. That's where we will get this second term, which is delta 1.618 times 1. Okay, so if I add these two terms, that will be delta plus 1.618 delta, or in other words, that will be 2.618 delta. So right here, when we are finding the x2, that will be x0 plus 2.618 delta, and that is coming from the equation that we are getting here. This is how we select x0, x1 and x2, which are the three initial sample point, and then we look for the three cases that we have discussed, whether to move right, whether to move left, or whether to move positive, or whether to move in the negative direction, and or if the third case where the optima is bounded, then we stop, right, and that is what is done. The only thing that changes in the Fibonacci sequence is how you locate the x0, x1 and x2, and that is slightly different than the Swan's method. Otherwise, the case specific scenarios are exactly the same as the Swan's algorithm. You will always fall into those three cases, and you have to look for those three cases to see whether you should move right, left, positive, negative, or you have basically located the optimal solution. Okay, so let's take an example problem, the same example problem that we solved using the Swan's method, and see how does the Fibonacci sequence method will work and how it will, act on the same problem. So again, that's the same problem, and we initially begin with x0 equal to 1 and delta equal to 0.5, and that's how we started. Now let's use the steps that are there in the Fibonacci sequence. So if I go ahead in that direction, then my x0 equal to 1, and at that function I have sampled the function value, and that fx0 came out to be 18. How? Because you can put 1 here. So 2 times 1 square plus 16 divided by 1, that will be 18. That's how we are sampling the function, this function at x0 equal to 0. So we are substituting the x0 equal to 1 in this whole thing, and that's how we are getting this function value. We know that the x1 is going to be equal to x0 plus delta, or which is equal to 1.5, and this is still very similar and in fact same to the Swan's method. But as you will see, the x2 value will be slightly different and different than the Swan's method. Okay, so once we found out the x1, which is x0 plus delta, and since delta is 0.5, we added that and we got 1.5. We will now substitute 1.5 in this equation. 2 times 1.5 square plus 16 divided by 1.5, and that will give me the function value of 15.167, and so fx1 will be equal to 15.167. Okay. Now the interesting part, and this is the part which is differing from the Swan's algorithm. We do not have x0 minus delta, we have x2, which is x0 plus summation of j equal to 0 to 1 delta 1.6j, right, which is equal to x0 plus 2 times del 2 x0 plus 2.618 delta. So if you add delta value of 0.5 and you simplify that, then x2 location will be 2.30. Now we will substitute this 2.309 in this function. So this will become 2 times 2.309 square plus 16 divided by 2.309, and that's how we will get the function value at x2, which will come out to be 17.59. Now if you look what is happening, on the x-axis you have 1 here, okay, you have 1.5 here, this is delta, and you have, this is essentially 1.5 here, and then the next value, which is basically, let's call this as x0, let's call this as x1, and this is x2, this one is 2.309, right? So you can see that this distance is not equal to this distance, and that's the difference in the Fibonacci sequence method that you do use to generate the sample point itself. Now the functional sampling is different from the sample points where you're generating. Now what we need to do, we need to see what is the nature of the function at three of these values, right? Now you will see that essentially the function value is something like this, right, where fx1 is 18. So right here we have 18. At this location, fx10, this is 15.167, and fx 2.3, there is 17.59. So essentially we are in case 3 of the 3 cases that we should be working on, right? So in this case, right, the function values are essentially lying at the 3 different locations that are out there. So we belong to this case 3, and so what we have done, we have essentially found out the intervals where the optima is bracketed, and in that case our solution or the bracketing solution will be 2.309, because that's where within this two interval is where the optimal solution is going to lie, right? And so this algorithm, or the Fibonacci sequence algorithm with the same initial point and the same delta, is going to converge in a single step, whereas if you have seen the Swan's method, we took 2 iterations, and that in 2 iterations we converged, and that's the main difference between the Swan's algorithm and the Fibonacci sequence based algorithm for bounding the interval or finding the interval in which the optimal solution lies for a single variable problem. So now again we have seen that we have essentially found the solution, and what we have discussed in this class is, first of all, we have mainly focused on unconstrained optimization problem. As you have seen, we have not taken any constraint on the optimization problem. More importantly, we only focused on a single variable problem. So the x, there was no x1, x2, x3 and so on. There was a single variable that was involved. And then at the beginning we discussed that there are 2 main phases. One is the interval bounding, and once you bound the interval, then you go and look for and search for the optimal location. So in this lecture we mainly covered the 2 different types of algorithms, which are Swan's method and Fibonacci sequence based methods for finding the bound for a single variable unconstrained optimization problem. With that, we will stop. Thank you. And in the next lecture, we will learn about actual algorithm, which is a very famous unconstrained optimization algorithm known as golden section algorithm, which is a method to find and locate and search for the optimal solution once the interval has been bounded.